Hello folks, back by popular request is another Murphy video. If you're saying to yourself, I never asked for this, then sorry. But nonetheless, I'm going to finish off this chapter with section 5.3, Conditional Probability and Independence, and I'll try to keep this video as short and concise as possible. But keep in mind, it's always a good idea when we look at a problem for you to pause it and consider it first before being presented with the answer. Also, as usual, here's the first page where I talk about the objectives, which again is better on reflection when you're looking at when you're studying, because I'm going to address these things one at a time as we go through it. So let's go through it. So in at least one of my classes, a student had asked when we were talking about independent probability, where if you recall, we just multiply the probabilities of each independent event. Someone asked, well, what do we do when they're not independent? How do we do that, or do we just multiply, and does it work out the same? The answer is yes, we do just multiply, but second of all, it doesn't work out quite the same way because we need to consider how the first event occurring affects the probability of the second event's outcomes. So for example, I randomly select two students from a class of 28. There are 16 boys. What's the probability that they're both girls? Let's assume that every student in this class identifies as either a boy or girl, and then we need to consider what happens after we make our first selection of a girl. What we need to consider is what our second selection would look like. Our second selection is going to be influenced by the first one, and for this reason we need to evoke something called conditional probability, which is to say, what's the probability of B occurring given A has already occurred? This thing right here means given, essentially. So what's the probability of picking a girl given that I already picked a girl? Well, the probability that I pick a girl the first time around is 12 out of 28 because that's how many girls are in the full class. But then with my second selection, the sample size has depleted because I'm not picking the same student twice. So I now have 27 to select from after the first one's been selected. And there's now one less girl to select too because there was already one selected with the first pick. So if you multiply these probabilities together, you get 0.17. I draw 3 cards from a shuffled deck without replacement. Replacement is putting them back. So if I'm doing it without replacement, that means after I make my selection of a card, I'm not inserting it back in the deck, which means I can't pick it again. So find the probability of a red card, then a queen of clubs, and then a black ace. So to write this out in the way that I wrote out this whole conditional probability notation is really annoying and long here. It's the probability that I get a red times the probability that I get a queen of clubs given I already picked a red, and then times the probability that I get a black ace given my other two selections. So if I neglect this here and just consider this, the actual calculations here should make sense. I know half the cards are red, so I could have written this as 1/2, but I'm choosing to work with the denominator of 52 to show how the sample size depletes after each selection. There's 26 red cards in a deck of 52. There's only one queen of clubs out of the remaining 51 cards, and there are 2 black aces, the clubs and the spades, in the deck remaining. So I multiply these together, and I get something very, very small, which makes sense because this is a very specific request for a problem. So yes, I do still use CDs in my car. I have an old car, and 4 of them are actually from the band Opeth. Here's the 4 CDs I have. What's the probability that if I randomly grab 2 of them, they're both from this band Opeth? So again, I could work it pretty much in the same way as the previous ones. It's very similar to problem number 1. I get 0.03. I don't know how familiar with combinatorics you are from Algebra 2 or whatever else you've done in math before. Combinatorics is the whole like permutations and combinations thing. But just know that if I did consider it that way and say like, how many different ways can I select 2 Opeth CDs? That's 4 choose 2. And then how many different ways can I choose 2 CDs out of my entire collection? That's 20 choose 2. And for what it's worth, this comes out to the same thing. So we're not actually going to talk about combinations and permutations this year, but it's always nice to know that other branches of math are consistent with what we're doing here. So just to recap some of our formulas and to talk about exclusivity versus independence. The notion with exclusivity is like what we talked about last time, where the formula, if they're exclusive, is you just add them up. But when there is not mutual exclusivity, which is to say that there can be some overlap between 2 events, what we have to do is add the second part to subtract the overlap. This is the one that's going to be on your formula sheet, not the top one. And like we talked about last class, the top one is kind of included as a subset of this one, because if there's no overlap, then P of A and B is just 0. But there's no need to write that on the formula sheet, so they just condense these 2 things into one. There's something very similar that happens when we talk about the notion of independence, where we know this one, where it's actually just referred to as the multiplication rule in terms of the AP syllabus, where the probability of A and B is just the probability of A times the probability of B. That's when they're independent. But when they are not independent, which this is now on your formula sheet, at least the top one here, the probability of A and B occurring is one of these, but let's stick with the first one. The probability of A times the probability of B given that A has already occurred. So, kind of like the first situation, to list both of these things would be redundant because they essentially are the same, but they don't look the same. It looks like this is here and this is here. But we need to ask ourselves, if they're independent now, if B isn't being influenced by whether or not A occurs, then we would expect these two quantities to be the same. Like if B is not affected by A, then the probability of B occurring is going to be the same as the probability of B occurring given A has already occurred. Like if B is the probability that I roll a 1 on a 6-sided die, it's just 1/6. If I tell you that A is I flip a coin and it gets heads, then me getting that heads isn't going to change the probability of B from being 1/6. So these two things would be equal when we're looking at events A and B being independent. So to get that down to the notes, when A and B are mutually exclusive, this overlap region is 0. And when A and B are independent, then the probability of A is going to be the probability of A given B, which is to say that B won't change the probability of A, and also vice versa. If I were to, let's see. Actually, you know what? I just realized I was wrong about something. This won't be on your formula sheet. This will, down here. If I want to solve for the conditional probability, essentially, imagine now I have this equation, this bottom one, and I want to, let me clear all this out actually, and I want to solve for this. In other words, I want this quantity on its own. What would I do? I would divide each side of this equation by the probability of B. If I divide both sides by the probability of B, I end up with this, and this is the equation that we actually see on our formula sheet. Not that there's any big difference between these. It depends on the way the problem is presented, which one of these forms we might want to utilize. Like if I'm trying to find the probability of A and B, then it makes sense to look at this box and calculate things this way by plugging them in. But this is the thing that's listed on our formula sheet. Don't be thrown off. It's just another algebraic variation of the one that I have on top here. I often get asked, what's the difference between exclusivity and independence, or how do we deal with the two in our brains? Oh my god, that voice crack. I'm not restarting. You can make fun of me for that later. I attended a seminar one year from a statistician, like a pretty famous one named David Bach, and he used this example, which is to say I could think of exclusivity and independence in terms of how some high schoolers might handle a breakup if they're going to a dance or something. So let's assume there's a dance happening. There's some chance that each of these two people are going to go. Alice used to date Barry, and they're both considering going. The probability of A is the probability that Alice goes. I should say event B is the probability that Barry goes, or B is Barry goes. You get it. So mutual exclusivity would be a bad breakup, which is to say that if one person goes, then the other one doesn't. Barry learns from his friends that Alice is going to the dance, so he's like, oh, forget it, I can't look her in the eyes again. That would be the probability of A and B equaling 0. If one goes, then the other won't, which means A and B occurring, both of them being present, is just not going to happen. Note that mutual exclusivity implies that A and B are not independent because one event happening very much influences the other event happening. In fact, it makes it 0. The opposite here is also true. P of B given A is also 0. Independence, on the other hand, is like a pretty decent breakup. They're just like, whatever. Like, maybe they're not the best of friends. You know, you could insert whatever teen drama you want here to make this make sense. But imagine that, like, Alice is sitting at her house considering whether or not she wants to go, and then her friend, like Gabby or whatever, calls her and is like, hey, I just heard that Barry's going to be there. What do you think? So whatever chance she had of going in the first place, she learns that Barry's going to go, and she's like, whatever. That doesn't make her any more or less likely to go because she's over it, and the events are independent, which is to say Barry going is not going to influence the probability of Alice going, and then also vice versa. Note that this, similar to the last one, implies that A and B are not mutually exclusive, because knowing that they're independent means that the probability of A and B is just going to be the product of those things, which will not be 0, given that there's a non-zero chance that each of them will go. So there is some like overlap between these two things, given the last bullet point, but they're still very different and distinct properties of two events. It's important that you know the difference. All right, time to actually get to some work. So one of the ways that conditional probability, or any probability problem, could be presented to you is in the form of a two-way table, which we've definitely looked at in the past, just not with these types of calculations. So what I would do right now if I were you is pause it and take a second to read the problem and start to answer these questions, which first include actually filling out the table. I'm going to go now, though. If I were to take this information and look at the complements of some of the events and count down, I'd end up with this table. There are 81 games, 26 involved having tacos and a win, and so on and so forth. So find the probability that the Diamondbacks win, or there are free tacos. So we should remember how to handle or events, which is to say that we just add them up, but then we have to subtract the overlap, given that they're not mutually exclusive, which they're not, clearly. If I take all of these probabilities and jam them in here, I end up with 0.56. You also, if it's laid out in a table, could just straight up count things out. A win plus tacos would be this, this, and this. So if I count these up and throw them over 81, I end up with about 56%. And or if I just go with the 30 plus the 41, remember that what I've done is I've double counted the 26, so I have to subtract that. For the next one, find the probabilities that the Diamondbacks wins, given that there are free tacos. The whole given thing, what that does is that really restricts our sample space to only the situations in which there's free tacos. So if I just use the formula that's on the previous page, I end up with a nice, ugly compound fraction, but at least the denominators are the same. So they can cancel out and give me 26 out of 30, which is equal to 0.87. The formula is going to work. It's going to be consistent every time. And it's reliable, it's on your formula sheet, whatever. But it's not always the best way to do stuff. It's not always the most time efficient. So like I was saying before, given that there's free tacos, this last part of the sentence restricts my sample space to just the T column. So with that in mind, if I'm looking at a free taco game, if I'm looking at the 30 free taco games, and I want to know how many of them included wins, or what proportion of them included wins, that's going to be the 26 out of the 30, which just brings me right here. So, like, yeah, formulas are nice, and they're cool, and they work every time. But always remember, if it's laid out for you visually, that you might want to consider just using the table and seeing how the conditional probability, limits your sample space. 4, find the probability that there are free tacos, given that the Diamondbacks win. This is like the same sort of thing where instead of limiting it to the taco column, I could limit it to the win row and get that 26 out of 41 wins being free taco days. So here's the same information again. If I ask, are events W and T mutually exclusive? Hopefully your answer is no, like a very quick no, because here is them both occurring at the same time. That's 26 wins where people get free tacos. But then the notion of, are they independent? We've never checked this before. At least I don't think so. No, maybe we did in chapter 1. But anyway, here it is again. Are events W and T independent? There's one of two things that we can check. We can check to see if the probability of winning is the same as the probability of winning given it's a taco game, which is to say that the probability that tacos are handed out is unrelated to the wins. And I can do this just by checking the probabilities. 41 out of 81 games are wins. 26 out of the 30 taco games are wins. So it looks like these two things are not the same. And if I do it in reverse, if I look at T and T given W, I get different numbers, I get different fractions, but I come to the same conclusion, which is that these two things are not equal. What does this imply? This implies that they are not independent, and we should think of the opposite of independence not as dependence, but as some sort of association. In this case, I'm not going to say that getting tacos leads to a win. It's more likely the case that the confounding variable here that's responsible for this association is the fact that both wins and getting tacos are related to getting 6 or more runs. In fact, getting tacos is 100% related to scoring 6 or more runs, but you could also imagine getting a lot of runs relates to wins also. So no, it makes sense that there's an association between these and that they're not independent. The last thing to cover in this section is the notion of using trees, and trees are actually very good tools for deducing probabilities when it comes to conditional probabilities. So like usual, what I want you to do here is pause and consider this question, and maybe think about how we would make a tree to look at the branching possibilities, and how each of those branches would affect the probabilities of each of the other things. Or you know what, there's another one on the next page, so if you want to just watch this one first, that might be a good idea. But at least take a second to read the problem. All right, so how do I break this down with trees? Basically, there's two different student groups. There's the high schoolers and then there's the youngins. And 58% of the people selected from the study would be a high schooler, the rest would be young. So again, you look at complementary events in order to deduce that this is 42%. And then of the high school students, what's to say? 40% agreed that virtual learning was effective. And then what do the rest think? The other remaining 60% disagreed or did not feel that that was the case. If I look at the agree and disagree proportions for younger students, it's different. So we need to consider that when we look at the probabilities of things like, some of the further down ones. But the probability that I select someone that's young, Before I get into that, I guess one way to check our work, and we can do this now, what I would suggest doing is filling out the probabilities of each of these things, each branch of this first, because it helps to check our work in a way that I'll show in a minute. And it helps to kind of think what we're doing along the way. So if I take this 0.58, this is the probability that I select a high schooler. If I then multiply that by the 0.4, that's the probability that a high schooler agrees that virtual learning is effective. So this is essentially the probability of picking a high schooler times the probability of picking someone who agrees, given that they're a high schooler. And as usual with the multiplication rule, we just multiply straight across. And if I do this for all 4 of my branches in this tree, what I should end up with is 100% of my possible outcomes, which means when you take this sum, you end up getting, if you did it right, 1. Because we've now accounted for 100% of our sampled body here, and 100% of the possible outcomes if I select a random student and examine the probabilities of everything. So it's important to recognize what each of these branches represents. Like, for instance, let me make sure I don't give one away. Here, like this 0.33 represents the probability that I've selected someone who agrees. Probably that I selected someone who agrees given that they're young. So each of these branches going inwards would indicate some conditional probability that hinges on the previous branch. So just be aware of how trees work and what each of the numbers represents. And really the multiplication rule just takes us to the end and gives us something that should be mathematically consistent. If these don't add up to 1, then you got a problem. You should go back and check. But the probability that I grab someone young from the sample, that's 0.42. That's just laid out. The probability that I select someone who agrees, given that they're a high school student. Well, actually, I just labeled that. This is the 0.4. Wait, what have I done? Oh, that's wrong. No, an error. Probability that they agree, given they're in high school, that's 0.4. Sorry. I think I ended up changing the question without changing the answer. The probability that they're a young student that disagrees. That implies that they're young and disagree. So for this, I'd have to multiply the 2 probabilities together. This is the, let me do this in different color, I guess. Actually, let me clear all this out. This is the probability that they are young times the probability that they disagree, given that they're young, which would be the product of these 2 numbers, which gets me the 0.2814. The probability that they agree in general, whatever student I choose, agrees. I see 2 different options for this. There's the high schoolers agreeing, and then there's the younger students agreeing. So what I'd have to do is take these 2 numbers, which is why we calculate this in advance, and then add them up. So we're good. I guess I could have written this as the probability that they agree, given they're in high school, plus the probability that they agree, given that they're young. These are the 2 agree situations, and I would add them up to get the total number of, or total proportion of sampled people who agree. Also remember, this is only sampled people. Like, I wouldn't go on and extrapolate and say that about 37% of students agree that virtual learning works. Later on in this course, actually, we look at tools that allow us to take sample data and say, all right, to what extent can I apply this to a population? But we're not there yet. This last one is actually quite hard. The probability that a student is young, given that they disagree, which is to say that if I'm looking at the collection of all students and I choose a student who disagrees, that's my sample space, what's the probability that they're young? That's hard to do in this case, right? Because there's 2 disagrees, and it's tough to work backwards or look left in this branch. So maybe in this situation, if all else fails, what might be useful to do is look at our formula sheet. Everything that I had on whatever page that was with the formulas and stuff, that's all on your formula sheet, or at least I indicated what is. This is something that is. Conditional probability is. So our formula sheet says that the probability of, that's a bad P, probability of y given d is going to be equal to the probability that they both occur divided by the probability of D. So I could find each of these things. The probability that they both occur, that they're young and disagree, is this. This is our numerator. And the probability that they disagree would be, well, there's two groups of people who disagree. There's this one, and there's this one. So if I take the sums of those two things, that would give me my denominator. So out of all the people who disagree, out of the, what is this, like 62-ish%, maybe like 63, out of the 63% of people who disagree, the youngs are the 0.28. So I would take that 0.28-ish, I would divide it by the 0.60, whatever I said, 0.63, and that would get me this final probability, which is to say, of all the people that disagree, about 45% of them are young. And yes, we could use complementary events here and say that of all the people that disagree, about 55% of them are older students. Whew, they can be complicated. So what I have on this page is another problem set. I feel as though it would be redundant, though, and this video is already getting quite long. And if you could do the previous page, you can certainly do this page. And I don't think you need me to give instruction on it. But what I will do is I'll say take a second to pause it and try it if you want. Then I'm going to just project the answers. So pause now if you want. And here's the answers. Here's the tree. And here's all the corresponding probabilities. Notice that I used some complementary event notation here to talk about either it rains or it doesn't, or whatever Jess is late or is not late. But yeah, here's the answers. So if you pause this to try it on your own, hopefully you got this. Otherwise, maybe try it on your own some other time. Start from scratch. Just open the blank notes template and try it then. But this is it. This concludes our probability chapter. So more information to come in the near future. Thanks for watching.